In our last two videos, we learned three cascade compensators. They're PI controller, PD controller, and PID controller, which all belong to the same family. In this and the next video, we're going to learn a new family of cascade compensators. The first one we're going to learn today is called lag compensator. Lag compensator is an approximation to a PI controller, which serves to reduce the steady-state error without significantly affecting the time response. The transfer function of a lag compensator takes this form. It has a gain denoted as Kc, it has a zero at negative Zc, and it has a pole at negative Pc. To make a lag compensator to work as expected, the zero and pole need to be very close to each other, and the gain of the lag compensator needs to be very close to 1 or equal to 1. Now let's see how a lag compensator works. Let's assume a system in the unity negative feedback configuration that does not contain any compensator. Let's also assume the system is a type 0 system. Then the static error constant that's finite non-zero is the position constant, which is equal to the limit of the transfer function on the forward path as s approaches 0. The steady-state error due to a unit step input is finite non-zero for this type 0 system, which is equal to 1 over 1 plus kp. And now we're going to introduce a lag compensator to the forward paths, which will be placed in cascade with the existing system's gain and plant. So here is the lag compensator with the gain has already been chosen to be equal to 1, with 0 at negative Zc and the pole at negative Pc. The compensated system with the lag compensator is still a type 0 system. Therefore, the position constant is still finite non-zero. So we have the position constant after compensation, denoted as k sub pc, is equal to the limit of the transfer function on the forward path as s approaches 0. Now I have the lag compensator transfer function goes into the limit. With the position constant evaluated, we can now estimate the steady-state error of the lag compensated system. So the steady-state error due to a unit step input is equal to 1 over 1 plus the position constant k sub pc. If we want the lag compensator to reduce the steady-state error, which means that we want E prime step to be less than E step, then the position constant after compensation, k sub pc, needs to be greater than the position constant before compensation, kp. This means that the ratio of kpc to kp needs to be greater than 1. And I have already substituted the expression for kpc and kp into the ratio. If you simplify this expression, you would have kpc to kp ratio is equal to zc to pc. This indicates that in order to reduce the steady-state error by introducing a lag compensator, we need to make zc greater than pc. If you go through the same process for a type 1 or a type 2 system, you will have very similar results. For a type 1 system, the ratio of the velocity constant after compensation to that before the compensation is equal to zc to pc ratio. And for a type 2 system, the ratio of acceleration constant after compensation to that before compensation is equal to the same zero-pole ratio. So whether you're working with type 0, type 1, or type 2 system, for a lag compensator to reduce the steady-state error, you just need to make the gain of the lag compensator Kc equal 1 and make Zc greater than Pc so that the static error constant of the system will be increased, which leads to the reduction in steady-state error. But making Zc greater than Pc contradicts with one of the requirements that we introduced earlier for a lag compensator, which is that Zc has to be very close to Pc. Before we address the contradiction, let's think about why Zc has to be close to Pc. We know that by introducing a lag compensator to a system, the root locus of the system is expected to change because there is an additional open loop 0 at negative Zc and additional open loop pole at negative Pc. If we do not want the time response of the system to be significantly affected by introducing a lag compensator, then we do not want to reshape the root locus. The only way to avoid the root locus of the system from being reshaped by the lag compensator is to let the effect of the 0 at negative Zc on the root locus be canceled out by the effect of the pole at negative Pc on the root locus. To achieve the cancellation, Zc has to be close to Pc. Then how can we satisfy this constraint while at the same time making Zc greater than Pc? Well, let's explore a few combinations and see what we can do with what we have. Let's say we want to achieve 10 for the ratio of Zc to Pc. And here I'm giving you 3 combinations. One with Zc being equal to 100, Pc being equal to 10. The ratio definitely satisfies, however, they're not close enough. The second combination I have Zc equals 10 and Pc equals 1. They also satisfies the ratio of 10, but they're still not close enough. If you compare the second combination with the first combination, we definitely consider that Zc and Pc are getting closer to each other as opposed to the first combination. For the third combination, we have Zc equals 1 and Pc equals 0.1. Ratio is satisfied, and we're definitely seeing Zc and Pc are getting closer. So now we see that if we want to achieve the desired ratio while at the same time making Zc and Pc close to each other, we just need to make both close to the origin. One last and explicit constraint on picking Zc and Pc is that you do not want to make Zc or Pc negative. The reason you want to have both Zc, Pc positive is to avoid introducing an additional branch of root locus in the right half plane so that you're not introducing a right half plane close to pole that makes the system unstable. Now we understand how a lag compensator works. Let's see it in an example. The system given in example 9.4 is currently operating with 10% overshoot when K is set to 30.4. We're asked to design a lag compensator such that the steady-state error is improved by a factor of 10 without increasing the percentage overshoot significantly. So we want to reduce the steady-state error by a factor of 10 while keeping the percentage overshoot under 10%. Here we have some of the results of existing system or uncompensated system. We have Kp already evaluated to be equal to 1.52. So this is a type 0 system. We have already done the simulation on the time response, which reveals a steady-state error of 0.397, and we have a percentage overshoot that is 9.64%, which is almost equal to 10%. What we wish to achieve with a lag compensator is to reduce the steady-state error to 0.0397 while keeping the percentage overshoot still under 10%. What you're seeing here is the block diagram of the system with the lag compensator already placed on the forward path. I have already combined the gain of the original system K with the planned G of S. Here we're going to choose the gain of the lag compensator to be equal to 1. We just need to figure out the values for ZC and PC. In order to design for ZC and PC, we need to know the ratio of the position constant after compensation to that before compensation. So let's do that first. The steady state error after compensation is denoted as E sub SSC, which is 1/10 of the original steady state error. That comes out to be equal to 0.0397. The system with the lag compensator is still a type 0 system. Therefore, the steady state error after compensation can be evaluated by the position constant, but it's a new position constant, which is denoted as K sub PC. Using this equation, we can calculate the position constant after compensation. According to what we learned earlier on this slide, we have ZC to PC ratio is equal to 15.91. Then we can use the ratio to guide us to choose the values for ZC and PC. Here I've chosen PC to be equal to 0.01, ZC comes out to be equal to 0.159. Then the lag compensator will have a transfer function that looks like this. Now with the designed lag compensator, we're going to use MATLAB to simulate its performance. Here in MATLAB, I have already defined the plant of the original system, G, the gain of the original system, 30.4, and the lag compensator. If we multiply G with K and G lag, then we have the open loop transfer function after compensation. Here we're going to use GC to denote. And then let's find the closed loop transfer function, TC. Since I want to see the step response before compensation on the same graph with the step response after compensation, I'm also going to define the closed loop transfer function without the lag compensator. All right, so now let's plot these two step responses on the same graph. According to the simulated step response, for the compensated system, we have a final value of 0.96, which gives us a steady state error of 0.04. The bump over here does not overshoot above the final value. Therefore, the percentage overshoot of the compensated system is equal to 0. Coming back to the table, I have already filled in the information that we have already obtained about the compensated system. We have the KP, which has been significantly increased. We have a steady state error of 0.04, which is about 10 times less than the original steady state error. And we have 0% overshoot, which is less than 10%. As far as the overall gain, since the lag compensator does not introduce an additional gain, then it stays the same as 30.4. For the remaining part of the table, I need to go back to MATLAB to find the closed loop poles and zeros. The compensated system has 4 closed loop poles. 2 are complex, the other 2 are real, and it also has a closed loop 0. When I put the closed loop poles and 0 in the table, I chose the complex poles to be the dominant closed loop poles. So for the closed loop pole at negative 10.38, it is more than 5 times away from the j omega axis than the dominant closed loop poles. Therefore, this closed loop pole is going to have very negligible impact on the time response. For the closed loop pole at negative 0.106, which is definitely closer to the j omega axis than the dominant closed loop poles, if the effect of this closed loop pole on the time response cannot be canceled out by a closed loop 0, then this closed loop pole at negative 0.106 will have a greater influence on the time response. Then let's see if the closed loop 0 at negative 0.159 can be considered as a cancellation with the closed loop pole at negative 0.106. If we just compare the values, we would consider that this closed loop pole at negative 0.106 cancels the closed loop 0 at negative 0.159. However, the simulation reveals that second-order approximation is not valid, which indicates that the zero pole cancellation is not good enough.